Okay, thank you very much, Johan Guk. And first of all, yeah, it's a pleasure to give a presentation. I deeply regret I cannot visit MPL. I would have loved to come. I was there, I think, about 2 years ago, and I would have very much liked to see how things have evolved since then. And of course, I have a lot of good colleagues there and also former co-workers. And so I'd like to thank you and your colleagues for giving me the honor to present this distinguished lecture series. And the topic I've chosen today is to tell you about work on photonic chip-scale frequency combs. And before I get started, I would like to mention something which I find particularly important, and that is really the work I'm presenting is to really the work of a big team. And I like to in particular thank my former members, one of them who is in the audience here, like Pascal Delhaye, but there's also others like Albert Schließer, Ivo Verhagen, Olivier Azizi, Samuel de Leglis, Harun Go, and Dal Wilson, and Tobias Herr, who recently moved to Hamburg. And I also like to particularly thank collaborators, particularly the late Michael Gordetsky from RQC, with whom I've cherished a lot of the results I'll be presenting today. And of course, I'd like to also thank up front actually all the funding agencies that make possible this work, in particular the ERC and also sources from US funding. So I'd like to start out by telling you a bit about the field of optical microresonators and optical microcavities. And that's really what has allowed a lot of new research fields to blossom, and in particular also the example I give today of on-chip frequency metrology. So the field of optical microcavities is quite old, and the ideas are extremely simple. The ideas are effectively centered around the central theme of confining light in very small volumes for extended amounts of time. And already back in the 90s at Bell Labs, there was the first work of using 3.5 semiconductor processing to generate small microresonators at the microscale. And the challenge traditionally has been to fabricate structures that have sufficiently high quality factor, so sufficiently low loss to confine the optical light. And here a very important development was made in the late 80s by Braginsky, Gordetsky, and Ilchenko, who observed that you can observe ultra-high Q, so quality factors of hundreds of million inside glass microspheres. And that kind of triggered off a research in the area of high Q microcavities. Now, even though these structures are very simple, the fact that you can find light for on small volumes for long amounts of time, in particular, allows to dramatically enhance nonlinear phenomena. And as we know today, nonlinear optics is really a key force both in science and technology alike. And so to give you some examples, nonlinearities of materials of either second order or third order are used for entangled photon pair generation, as used for QKD. Something actually Ile Quantique here in Geneva, not far from my home place, is commercializing for quantum cryptography. Nonlinearity is also used to generate squeezed light, and squeezing is not only of scientific interest, but in fact it's really driving the next generation of gravitational wave observatories, such as LIGO. And last, nonlinearities are really underlying the spectacular advances of frequency metrology, which have been unlocked by supercontinuum generation. And evidently, one of the pioneers is MPL in this subject. Now, what microcavities have allowed to do is revisit this field of nonlinear optics, but now taking advantage of the fact that we can make structures that are microstructured at the nanoscale and achieve very large photon confinement. And I show here kind of an historical slide, and this is work that I did at the end of my time at Caltech with Kerry Vahala, and it shows one of these examples of what happens when you confine light for extended amounts of time in small volumes. And these were toroidal microresonators at the time, and what they embody is again this idea of confining light. Here, quality factors of more than 100 million could be achieved, but now in volumes that are on the microscale. And this is allowed not only to enhance the radiation pressure forces, but also the intensity of the light field itself. And so on the one hand, one can rediscover known physics. So one can rediscover a lot of phenomena such as Bruin scattering, Raman scattering, or the Kerr nonlinearity. But also one can observe phenomena that had not been predicted and that are still surging or that are still being studied to date. And I'd like to give two examples. So the first phenomena is radiation pressure coupling. So when you when you have confinement of light in small volumes, you can also enhance the radiation pressure. And though these forces are very faint and generally have been perceived as not being observable in macroscopic objects, they can couple, okay, mechanical and optical degree of freedom. And that's today firmly established. It forms part of the field of cavity optomechanics. And these microresonator have been kind of a system by which this physics could be explored, by exploring the optomechanical coupling that naturally occurs in any optical microresonator. Now, another interaction that one can study in these microresonators is the Kerr nonlinearity. And again, the Kerr nonlinearity is very well known. It's the underlying process that gives rise to cell phase modulation, supercontinuum. But what's interesting in the context of microresonators, and that's really the topic of my lecture today, is that this process can allow optical frequency combs to be generated, and is now providing a framework to generate very compact chip-scale frequency combs that can make frequency metrology and also other applications ubiquitous. Now, so optical microresonators are really vehicles for these two fields. You can study, as mentioned, quantum optomechanical phenomena that result from the coupling of light and mechanical motion, where in addition to the optical degree of freedom, you explore the microcavity as a mechanical element, or you can use them to generate optical combs via the Kerr nonlinearity, which is the subject of today's talk. Now, before continuing and discussing how optical combs can be generated in microresonators, I'd like to briefly mention, okay, also other areas where microresonators are now starting to play a very interesting, important role. And one is the field of cavity electrophoton optics, where you couple actually electron beams to optical fields. And we've recently started working in this area with Klaus Ropers from Göttingen of coupling whisper and gallium modes actually to free electrons. And likewise in the field of cavity electro-optics, where you replace the mechanical oscillator by a microwave field and then rediscover the optomechanical physics, the optomechanical resonators provide unsurpassed coupling of microwave to optical photons. And that's a very large kind of or nascent research field today that's also present at MPL. Now, to give one example of the things I will not talk about, I just want to show one slide on some of the latest ideas that are in the area of optomechanics. And what I'd like to show here is an example where an optomechanical sensor is realized using a photonic crystal microresonator, which is coupled to a strain-engineered nanomechanical oscillator, where now we can have quality factors of close to 1 billion at room temperature. And what's shown here is actually on the lower part of the graph is a ring down, okay, of a nanomechanical string that has a ring down time of more than 2 hours, corresponding to a quality factor of exceeding 700 million. And those systems now are so coherent that when coupled to optical cavities, one can observe room temperature quantum optomechanical phenomena, such as polymotive squeezing, feedback cooling to the ground state, or Seidman asymmetry. And so again, here the microresonators again play the important role of the transducer. Now, after this kind of more general introduction, let me really focus on what I'd like to share with you today, and that is the field of optical frequency metrology. So optical frequency combs are a truly revolutionary technology that was developed by Ted Hensch and Jen Hall. So Ted Hensch already in the 70s thought about using mode-locked lasers to measure optical frequencies, but really took the invention of supercontinuum of photonic crystal fiber to make that dream come reality. And so in 1999, the first phase coherent links from RF to optical were demonstrated. And those utilized photonic crystal fiber to broaden, okay, a pulsed laser into an octa-spanning spectrum in order to implement a technique called self-referencing, whereby the optical comb that spans an octave, okay, allows the measurement of the so-called Kerr envelope frequency by simple non-linear optical means, where you double the red end of the comb and superimpose it with the blue end. And so this really unlocked a new way to measure optical frequencies. And the way optical combs function is they connect an optical frequency to two radio frequencies. One is the Kerr envelope frequency, so the opposite of the comb, and the second one is the repetition rate. And so the important part of this equation is that you link an optical frequency on the left-hand side to two radio frequencies. And by doing so in a rigid manner, what you can construct is either an optical frequency synthesizer, whereby you take a stable RF frequency and from it generate an optical frequency, or you can use this device as a divider, okay? So what we call optical frequency division. So you start out with a very, very stable transition, for instance, an atomic transition in ion, and then use the optical comb to divide that down to the radio frequency domain. And that's precisely the integral part of any optical clock to date. It's the clockwork that allows you to take a transition that lives in hundreds of terahertz and multiplex it down into the RF domain. And so clocks is really benefited from optical frequency combs, but combs are used in many more areas than that. They're used now in timekeeping, spectroscopy, even in astrophysical spectrometer calibration. Now, optical combs are a commercial technology. So Ted Hench at MPQ has spun out of his lab Mendel Systems, and today you can have an optical frequency synthesizer in your lab based on typically fiber mode lock lasers, and that provides you this gearbox from the RF to the optical. And you can again run it in this two-way fashion, either as a synthesizer or as a frequency divider. Now, what I'd like to tell you about today is research that led kind of to their serendipitous discovery that you can also make optical combs that are much more compact, access high repetition rates and broad spectral bandwidth using what we are now known as dissipative Kerr solitons. And so what I'd like to tell you about is an emerging technology, that of microresonator frequency combs, also called Kerr frequency combs, where instead of using kind of mode lock lasers, we use nonlinearities in photonic resonators to generate the comb. And the key advantage and the prospects of this approach are that by using optical resonators, we can operate at vastly higher repetition rates, and this unlocks new applications, and I'll give a few examples. But also, it links optical frequency metrology to a completely different field, that of integrated photonics. And so we have the possibility to make combs using integrated photonic elements and thereby also combine it with further electrical or optical functionality. And that really could make frequency comb metrology ubiquitous. Now, so the process that is underlying the optical comb generation process is parametric oscillations. And again, I apologize for those who are very well familiar with this, but I still thought to have some very fundamental slides here. So the process we're using to generate an optical comb is just four-wave mixing. So we annihilate two pump photons and generate signal at idler. And evidently, because of energy conservation, okay, the excess frequency of the idler needs to be compensated by reduction of the frequency of the signal. So thereby you create two equidistant sidebands. And that process is very well known, not just in optics, also in fact in the field of superconducting circuits. So there it's called Josephson bifurcation amplifier or Josephson bifurcation, and leads to generation of photon pairs. Now, one interesting aspect is that this process, opposite to conventional laser, scales with 1/q squared in terms of threshold. And that is because the gain is intensity dependent. So it's a double benefit of having a low loss optical cavity. And in microresonators with quality factors of hundreds of million and mode volumes of 100 lambda n cubed, you can reach threshold powers of just a few microwatts. So these are exceptionally low, just a fraction of the power of a laser pointer. So the process, again, generates two sidebands, and this process, by virtue of non-degenerate four-wave mixing, can cascade and thereby provide an optical comb. Now, so this was first described already as more than 10 years ago in 2007. Actually, it was thesis work by Pascal Delhaye. Another way to view this process, again, linking back to the community of superconducting circuits, is really it's a bifurcation amplifier. So the threshold for the parametric oscillations is reached whenever the Kerr-shifted cavity tilts are more than a line width. So if you have a linear cavity that's cold, you just have a Lorentzian buildup factor. If you also now have the Kerr nonlinearity, it will shift the frequency of the cavity proportional to the intensity. Okay, and there's a region where the cavity becomes bistable, and it's that bistability that provokes the formation of sidebands that one can observe here in the output spectrum. So this process can give rise to the formation of optical frequency combs, and thereby provide a way to generate combs with very high repetition rate. Very high meaning here, typically anywhere from tens of gigahertz, even all the way to terahertz. And even though no pulses are fought in this process, still the waveform that is generated is stationary and fully coherent and gives rise to an equidistant optical comb spectrum. Now, this process has been observed in many different resonator geometries. So Kerr frequency combs have initially been studied in silica resonators, but they have since then proliferated many platforms that in particular include also CMOS compatible platforms, in particular silicon nitride, a platform I'll introduce later. But also in more recent time, this Kerr frequency comb generation process has been extended to 3,5 compounds such as aluminum gallium arsenide, gallium phosphide, and even materials that have a Chi2 nonlinearity such as lithium niobate or gallium phosphide. And so there's been a lot of advances in terms of different platforms where these combs can be generated. Now I'd like to tell, again, a bit more about the physics that gives rise, that is underlying this optical frequency comb generation process. And despite the simplicity and intuitive appeal of parametric oscillations, the actual process by which combs are formed is vastly more complex. And it has to do with the fact that any cavity will have some residual dispersion. In this slide here, denoted as D2. So this is the walk-off of the free spectral range. Kappa is the cavity decay rate. And in an actual microresonator, what can happen is that the first pair of sidebands actually are very far away from the pump, very far away in terms of free spectral ranges. And that means while the initial comb can be fully coherent and can proliferate, what happens at higher pump power is that higher order processes, and in particular non-degenerate 4F mixing, can cause the primary comb lines to develop subcombs. And these subcombs in the high pump power regime can start to overlap. And that leads to actually a very, very non-intuitive situation where in one single cavity resonance, denoted here in gray, there's actually multiple mixing frequencies that occur. So we have many more kind of optical frequencies that are generated than just cavity modes that are involved in the process. Okay, so the intuitive idea of mode locking actually becomes very quickly obscured by this complex interplay of 4F mixing pathways. And this actually process caused for a long time, for about 5 years, many comb systems to actually have regimes where the comb are unstable. Okay, and this in particular is the case whenever the cavity line width is very large and the dispersion is small. That's in particular the case for many devices that are microfabricated that have typically much lower quality factors than the toroidal resonator I've introduced. And so here again is this picture where you have a cavity Laurentian and there's many optical frequencies being generated that are creating this very chaotic waveform inside the resonator. Now, what is very striking and I think a beautiful example is that nature can still find a way to synchronize all these frequencies. And that is by the formation of dissipative Kerr solitons. And so dissipative Kerr solitons have been first observed in crystalline microresonators. And so here is an experiment that was done by my former coworker Tobias Kippenberg now in Hamburg, where if one pumps a crystal resonator, one observes, okay, in the transmission spectrum first a noisy region. Okay, if one looks at the beat note of the optical comb, it's very broad. That's color-coded here, so it's indicative of a noisy state, so a comb that cannot be used for frequency metrology. But what was very striking in the experiments is that there was a region where a series of discrete steps was occurring. And these discrete steps occurred whenever the laser tuned exactly through resonance. And that is to say, where it reached this bistable region I described earlier. And in that region, in fact, the optical comb became fully coherent, and this could be witnessed by the repetition rate beat note that collapsed into a single RF. And what was happening here can be understood by simulating the process with 4F mixing, which was done in later work. And that is, what happens here is that inside the cavity, okay, pulse trains are forming in the bistable region, and each of these steps corresponds, in fact, to the successive diminution of a number of solitons. So if I play this video one more time, which was rather fast here, what you can see initially, a very noisy comb is generated, many interleaving comb lines, okay, many more than can be seen on the screen here, because there are multiple comb teeth underneath each cavity Laurentian. Until then, the system actually self-stabilizes into a single secant parabolic spectral envelope. Now, the actual waveform that's generated is a temporal dissipative Kerr soliton. And this can also be understood by going back actually and understand and considering the equations that underlie the 4F mixing process. So if one steps back and looks at the underlying equation, then what one has is that each mode that participates in the 4F mixing will have some loss, so some kappa. It will have there will be a pump term. Okay, so one of the comb modes will be cavity modes will be pumped, and then there is the 4F mixing terms. Okay, that give rise to the different processes, including degenerate and non-degenerate 4F mixing. Now, this is just a frequency domain representation of the equation, and it was pointed out by Matsko in early work that this equation can be also written not in the frequency domain, but the time domain. And in that case, this equation becomes actually very similar to an equation that's very well known under the name Lugiato-Lefever equation. It becomes a driven dissipative nonlinear Schrödinger equation. So the left-hand side actually of the equation here is very well known. That's just the equation, in fact, for conservative solitons. So there's a dispersion operator here, or dispersion, there's a nonlinearity, and then the temporal evolution of the envelope. On the right-hand side, there are terms, however, that are not conventional. Okay, and one of the terms is the pump laser, and another term is the dissipation and the detuning. And so that's why these solitons are also known under the name of dissipative Kerr solitons or dissipative solitons, because they are solitons that are living in a driven nonlinear system in the presence of an external pump. And so these DKS, as they're abbreviated, are really a double balance. On the one hand, there is gain and loss, or better to say parametric gain and loss. And on the other hand, there's the dispersion into nonlinearity. Now, these solitons, again, viewed from a more broader context, this Lugiato-Lefever equation is actually known since many decades. It was first formulated in 1987 by Lugiato in the context of spatial self-organization in nonlinear optical systems. And this equation itself had an even richer history going back to out of equilibrium thermodynamics, so non-equilibrium thermodynamics, where also pattern formation can occur. So one can view the formation of solitons in microresonators as a pattern formation process that occurs, okay, in the light field that's generated inside the optical microresonator. So, so to put these dissipative Kerr solitons into context, dissipative solitons exist in many systems. They exist in plasma physics, where have been first observed in 1974. They can also be observed in mode-locked lasers, and their spatial cousin, okay, can also be observed in cavities that exhibit or a nonlinearity, such as in the early work of Seghers and Ackermann. So after having understood kind of these solitons, let me mention a bit more about the physics and also how we can access the soliton physics. So what's particularly interesting and nice in the experiments is that this nonlinear dissipative Schrödinger equation is, on the one hand, we can numerically solve it. On the other hand, we have two control parameters. And one is the power that we inject into our microresonator. The second one is the detuning. And the detuning shown here on the horizontal axis and the power on the vertical, okay, they form a two-dimensional kind of phase space. And we call this stability chart. What we can do now is we can map out the different solutions of the Lugiato-Lefever equation and find regions where there's spatial temporal chaos, regions where there are stable solitons, and also regions where there are breather solitons. Now, in the last years, our understanding of this equation has become much better, and the stability chart I'm showing here actually is vastly simplified. There's regions where we can form soliton crystals, there's modifications due to Raman, modifications due to void mode crossings, but effectively what we are doing in these microresonators, we are simulating, so to speak, the solutions of this Lugiato-Lefever equation, and by appropriate choice of laser detuning, we can access different solutions. So let me just give an example. What happens if you go from the spatial temporal chaos into the soliton region? And so in the experiments, the way this would be done is one would scan the laser into resonance. One generate first parametric sidebands, so Turing patterns, or these early kind of Turing pattern type like combs that are fully coherent. The combs would then become nested, therefore leading to chaos. And when we tune through the cavity resonance, actually, it's in that moment that we can form dissipative Kerr solitons. And by continuing the laser scan, we can reduce the number of solitons. And we've also discovered a way to switch solitons deterministically into the single soliton state. And so the last state is effectively a secant symbolic spectral envelope soliton that's locked onto the pump field that also co-propagates actually inside the resonator. Now, these DKS have a number of interesting properties. First of all, they have very high repetition rates, just the inverse round trip time. That can be tens of gigahertz, even up to terahertz. The pulses can be very short. So the shortest pulses we have generated inside the cavity amount to just a few optical cycles. They can have spectral envelopes that we can tailor, and I'll give an example how this is done. And they also have a tunable pulse duration. And that's actually a rather non-intuitive feature I'd like to briefly highlight here. So here is an example of a dissipative Kerr soliton that is generated in the crystal resonator. And what you can see here is a so-called modulation response measurement. So what you see is that the laser, in fact, is detuned, okay, from the cavity resonance. It's due to the bistability. We're sitting on the lower branch. The soliton sits on the upper branch. And as the laser is detuned further, what we will see is that the soliton duration actually becomes shorter. And that is directly a prediction from the theory, which predicts that the larger the detuning is of the laser and cavity, the shorter the pulse will become. And so if we do this experiment, what we see is in this case that if we are detuned here by more than 25 kV line width from the cavity, we can generate actually solitons that are much shorter and much broader than if we were closer to resonance. Okay, and again, if one thinks about for a moment, it is extremely non-intuitive. So here the laser is detuned by more than 25 kappa away from the resonance. And again, this shows that the cavity is operating in a strongly bifurcated regime where the Kerr nonlinearity shifts the cavity by many tens of line width. Now, another surprising aspect of these solitons, and that really has given a lot of impetus to the field, is that solitons are surprisingly stable. Naively, you may think that a soliton requires this perfect one-dimensional system with very well-defined dispersion, no losses, no perturbations. But what is interesting is that nature always finds attractors. And so this is an example here of the actual mode structure of a crystalline microresonator. So it's far from a parabolic GVD. We have, in fact, many mode crossings that perturb the free spectral range, and these result from higher order modes due to imperfections. Now, what is interesting is that even in the presence of such mode crossings, the solitons can still form. And the way the soliton actually accounts for the presence of disorders is by emitting dispersive waves. So if one looks at this spectral envelope here of the soliton, one can see, okay, that there are certain regions where the power of certain comb-trees is enhanced, and these enhancements are exactly to balance, okay, the influence of local disorder in the dispersion. And so now what we understood is that the soliton formation process in microresonators, in fact, is surprisingly stable and doesn't even need to have a very well-defined dispersion. And it's an open question, okay, how much disorder they can tolerate. On a practical level, this has allowed solitons to be observed in many, many systems. And so solitons today can be generated in virtually any microresonator platform, both dielectrics, 3/5s, all the way to electro-optical materials, and repetition rates in the range of tens to hundreds of gigahertz have been shown, and also spectral bandwidth that cover even a full octave. Now, there's also a lot of new phenomena that were observed. Some phenomena very well known from the community of fiber optics. So a lot of the effects you can observe in supercontinuum generation, such as the Raman cell frequency shift, dispersive waves, can also be observed in the driven dissipative microresonator. But there's also phenomena that are fundamentally different. And to give you one example, you can also observe so-called soliton crystals, okay, perfect periodic arrangement of solitons. And those don't have a counterpart in the typical supercontinuum generation processes. You can also observe soliton molecules, soliton breathers that are catalyzed by higher order modes, counterclockwise solitons, and also kind of dark solitons that exist in a normal dispersion regime. And so over the last years, and I cannot cover this today, there's been a very, very good understanding of all the different processes that can happen in these optical microresonators. Now, what I'd like to focus a bit on in this talk is really going back to the vision I presented at the beginning. So can you make optical frequency combs truly ubiquitous? And even today, 20 years after combs have been introduced by Ted Tenge and Jen Hall, they're still mostly confined to laboratory environments, so to national labs and labs that have the kind of necessary funds to actually buy these type of instruments. And microcombs could be a way to make frequency metrology truly ubiquitous. And what I'd like to share with you next is work of generating dissipative Kerr solitons in photonic Chipscale microresonators. And for this, I'd like to introduce in particular one platform, and that's the platform of silicon nitride. So instead of making resonators from crystals or from glass microspheres, one can also make photonic resonators using chip-integrated materials. And one material that has caught the interest in the recent years has been silicon nitride. And so silicon nitride is actually not a new player in terms of nonlinear photonics. It's a material that's used already as an end capping layer in a CMOS process, typically as a diffusion barrier. But traditionally, it has been a very difficult material to work with for photonics. And the reason is that it's difficult to grow thick films of silicon nitride. Silicon nitride, as deposited by LPCVD, has high tensile strain, and so it tends to crack. And so most of the silicon nitride work up to about maybe 10 years ago was concerning very, very thin films. But for nonlinear photonics, what you need actually are thick films. And the reason is very simple. If you take a waveguide and you look at the effective index as a function of wavelength, any waveguide of any material will have a region where the light is very well confined, okay, inside the dielectric, okay, as depicted here. Then the refractive index will be that of the core. In contrast, when the wavelength is very large, okay, the light starts to delocalize, okay, and you would start to see the cladding. And in between these two, there's a sigmoidal kind of shape curve. And if you look at the second derivative, there's a region where the curvature here actually is positive, one where it's negative. And so one corresponds to anomalous GVD, one comes to normal GVD. And for nonlinear photonics, for soliton formation, you want to be in the anomalous dispersion regime. And so this requires your waveguides to confine the light very well. And for silicon nitride, this correspondingly means that you need to make at least film thicknesses of say 700 nanometer for a 1550 nanometer light confinement. That has been very challenging, but ways have been found to actually make that possible, and describe also one way as we go along. Now, silicon nitride is interesting for nonlinear photonics for a number of reasons. It has a very large transparency window. In contrast to silicon, it's transparent all the way to 500 nanometers, so they're visible. So you do not suffer from two-photon absorption. It also has a high effective nonlinearity, about a factor of 10 higher than glass, and the material is space compatible and can be deposited using standard semiconductor processing. And so in silicon nitride, you can also observe soliton formation. And in contrast to weak confinement platforms, what is very interesting is that the high nonlinearity allows you to observe higher order processes. And so one of these processes is called soliton-Cherenkov radiation. And in this case, what happens is that the soliton is so short that its spectral extent leaks into the normal dispersion regime. So you leave the regime where the group velocity dispersion is anomalous. And this causes the formation of a so-called dispersive wave, which is an oscillatory tail that is attached to the soliton. And this process, in fact, is very similar to the process that was observed first in fiber optics. That's called soliton-Cherenkov radiation, as proposed by Akhmediev and Magnus Carlsen. And it's also a process that allows, in particular, an underlying process for supercontinuum generation. So in the context of these Kerr microresonators, it allows to spectrally enhance the bandwidth, and in this case, create a boost, okay, in the long wavelength tail. So this has been so far just a theoretical prediction, and in fact, you can observe very good agreement actually with these predictions in silicon nitride photonic integrated resonators. And so here is one of our earlier kind of structures we generated. So it shows a pump at 1550. It shows a 2/3 of an octave optical comb with a repetition rate of about 190 gigahertz. And you can see here this dispersive feature, the dispersive wave that fits very well the gray line. And the gray line is now again the Lugiato-Lefever equation, where we've included, okay, the Raman cell frequency shift as well as higher order dispersion terms. And so you can see that we have a very, very good kind of quantitative understanding also of the spectra that we generate. And that provides a way also to engineer them and to make them particularly broadband. Now, this is just one process that can exist due to higher dispersion. There are many others. Examples include, for instance, dual dispersive waves. If you have 2 points where the zero dispersion point is crossed, you can also generate so-called platicons or interlocked switching waves if you go to the normal dispersion regime. Okay, these have also been observed in recent years. And in the presence of Raman nonlinearity, you can even observe the formation of so-called Raman-locked solitons, where a drive soliton generates another soliton via the Raman effect that is interlocked. And so there's a whole rich kind of variety of higher order dispersion phenomena, including the Raman effect, that can observe in these microresonators. And what we understand today is that the landscape for soliton formation is very vast. It not only encompasses the soliton formation process I've described, but also switching wave, which has actually a normal group velocity dispersion, and also regions, okay, that are neither normal, neither are anomalous, and just stabilized by higher order dispersion. So there's a whole zoology of waveforms that we can generate inside the microresonator, which are solutions of this driven dissipative nonlinear Schrödinger equation in the presence of both second order and third order dispersion. Now, what can you do with these soliton frequency combs? And what I'd like to do next is give you some idea of some applications where this DKS can be used, and where also the applications are different from those that can be explored with femtosecond lasers. And the first application I'd like to mention is actually in coherent communications. So shortly after we observed dissipative Kerr soliton formation in microresonators, it became very evident that these could become sources, okay, in coherent communications. And the reason is that you can match the mode spacing with the ITU grid, which is typically 25 gigahertz and multiples thereof. So in this experiment with Kish and Koos, what we did is we used two photonic chip-scale frequency combs, one on the sender side and one on the receiver side, to encode information. And while this was not a record in terms of the data transmission rates, what it did show is that microcombs actually can be used for future advanced coherent communications and also support higher order and modulation formats. So here a narrow line width laser is transduced into a series of replicas that owe the same phase noise as the pump laser and therefore can be used for sending higher spectral efficiency data. Now another example where also this high repetition rate in the tens of gigahertz is very advantageous is work that we did with Tobias Kippenberg, who is now at Hamburg. And this is a slide here from him where he shows that the dissipative Kerr solitons can be used for astrophysical spectrometer calibration. And the challenge in astrophysical spectrometer calibration is that to resolve with an astrophysical spectrometer the individual comb teeth, these need to be at least 10 gigahertz apart. And that is challenging with conventional fiber laser combs, but with Kerr frequency combs it is a very natural kind of repetition rate to operate at. And so in this work, what was shown is that one can achieve a spectrograph calibration that's sufficient, for instance, for the detection of Earth-like planets. And this is a very nice solution in the future for all existing spectrographs to replace argon-thorium lamps. Now, another application of the soliton microcomb I want to share is that of ranging, laser ranging. And here one can really make use of some of the salient properties of solitons. And so what I'd like to do in this slide is very briefly introduce to you coherent laser ranging. So coherent laser ranging, also known as FMCW LiDAR, is a technique which allows to detect both position and velocity of an object instantaneously. And the way this works is very similar to sonar, or that's also used by bats or dolphins. And what you do is you send out a chirp waveform that's typically triangularly chirped. And if this waveform is returned, there is on the one hand a delay. But if the object that the laser is reflected off is moving, there's a Doppler shift. And so if you now beat the incoming light with the outgoing light, then what you will have is you will generate an interferogram. And this interferogram will contain two frequencies, FU and FD. And from the difference in the sum of these two frequencies, you can determine simultaneously both position and also the velocity of an object. Now, coherent FMCW LiDAR is presently kind of a very hotly debated method. It's pursued by a number of companies, also including Intel, because in contrast to time of flight, the fact it has higher sensitivity, minimized interference, and also it allows you instantaneous velocity measurements. But there's a key challenge with that method. It's hard to parallelize. So you need many highly coherent lasers, which you can all chirp in a very precise manner to achieve very high pixel rates. Now, what is interesting about soliton microcombs is that you can ask yourself the question, what happens if you operate and generate a soliton and very quickly change the pump laser frequency? So you operate, again, here's this stability chart, and you very quickly modulate the laser frequency. What would happen to the soliton? And so naively, you may think that the soliton, being strongly perturbed, maybe it will just stop existing. But it turns out, actually, that solitons are very resilient against these changes. So the DKS, despite modulating the pump laser very fast, will still persist. And that actually provides a way to impart an initial chirp of the pump to all the comb lines simultaneously. Okay, and so what we have simulated here, and it becomes more clear in the next slide, is what happens as you tune the laser from position 1 to position 2. And what you can see here is that the comb has a slightly increased Raman cell frequency shift. But what is more important is that the repetition rate of the comb during this process remains almost unchanged. Okay, and this we can see by looking at the inside here. It shows that we have hardly any changes actually of the repetition rate, whereas we're chirping very strongly in a triangular fashion the pump laser. And so what is the cumulative effect of this? The cumulative effect of both these phenomena is that if we take an initially chirped laser field, chirped in a triangular manner to generate an FMCW signal, that chirp is now imparted onto the soliton. So the group velocity of the soliton remains unchanged, but the underlying waveform actually does change due to the chirp. And so translated into different language, what we're doing here is we are very quickly changing the Kerr envelope frequency, but keeping the repetition rate constant. And that actually is a very interesting and useful process, because that allows to turn the soliton microcomb into a massively parallel array of FMCW lasers. And so we have done so in recent work. So again, this is the setup. We chirp our pump laser in a triangular fashion. We inject it in our silicon nitride resonator. We generate, in this case, more than 60 channels. We send them out to different directions with a diffractive grating. We collect the light, interfere with the incoming one, demultiplex, and measure the individual channels. And in this way, what we could achieve is a coherent LiDAR that operated with 30 and more recent work 64 channels, and achieve actually megapixel per second measurement rates. And that's actually what you need to make video frame images with coherent LiDAR, which would be required, for instance, in applications such as autonomous driving. So, the soliton microcombs' surprising dynamics of being very resilient to the pump laser frequency changes actually turned out to be a very precious resource in FMCW coherent LiDAR. Now, moving further, again, I've just described that microcombs can be used for coherent LiDAR. So we've used that to also do some very simple images, like make an image of a logo here of our university. They can be used for coherent telecom. They can be used to make very, very compact turnkey synthesizers. This is work we did with John Bowers. And also one can endow the solitons with further functionality, such as piezoelectrics for fast actuation. And but one question I have not addressed is, what does it really take to bring these microcombs into applications? And that is not just the application, but really one of the key questions is the power. So many of the applications I've just described to you, they use in the lab lasers with tens of watts of power. And those power levels are simply not compatible with on-chip lasers as they're used today in data centers. So the question is, how can you access these nonlinearities, the soliton physics, at just a few milliwatts of power to truly make very compact photonic integrated circuits? And this is the last part of my talk, and I'd like to highlight what are really the challenges in integrated photonics. And so if you zoom a bit out and take a look at the broader field of photonics and optics, there's one thing you will realize, and that is that optical losses in fiber optics are just remarkably small. So today, the very fact that we can have this conversation is due to fiber optics. It's due to the remarkable work of Charles Cow and others that led to losses that are below 0.5 dB per kilometer in silica fiber. And silica fiber is still unsurpassed in terms of transparency. If you look at integrated photonics, despite almost 2 or 3 decades of research in this field, and despite integrated photonics are being used in data centers, the losses of silicon photonics up to a few years ago were 1 dB per centimeter. So there is a disparity here by many, many orders of magnitude between what you can achieve in optical fiber and what you can achieve in integrated photonics. And a rightful question to ask is this fundamental? Or is there any reason why one can't decrease the losses in integrated photonics? And a lot of the losses in integrated photonics have very mundane reasons. And the primary way in which integrated photonics today is manufactured is subtractive processing. It is using thin films and etching thin films. And that inevitably leads to roughness. In addition, one is limited just by the material composition. Now, if one can reduce the losses of integrated photonics, then one can significantly reduce the threshold for parametric oscillators, okay, from today tens of watts to really just milliwatts. What I'd like to show you now is work that has allowed to bring the threshold of these parametric oscillators and these Kerr soliton frequency combs down from a watt, as it was a few years ago, to now below 1 milliwatt, which allows even heterogeneous integration with 3/5. And this has been possible by revisiting some of the fundamentals of how these waveguides are fabricated. And so what we came up with is a new fabrication process to generate very low loss photonic circuits. And this process is inspired by the copper damascene process. That's why also I show here this ornament from Damascus. So how is this ornament made? It's made by taking a preform, okay, that has corrugations, then filling the corrugations, in this case with copper, and then polishing it. And that copper damascene preform method is also used, in fact, in VLSI, some very large-scale integration in any CMOS processor. So in our computer right now, if you were to look at the cross-section of your Pentium or your AMD or ARM processor, what you would find is interconnects. And this is exactly how the interconnects are made. It's using this process. It's using a preform, filling it, and polishing. Now, this process we have emulated for photonics. And so what we've done is we've taken this process, but now we've done two important modifications. The first is we use a dielectric. And the second one is we reflow the preform. And reflow meaning we heat it up to make it very, very smooth without any roughness. That process works very well. So this is an example of two waveguides. And for the experts in the audience to know a bit nanofabrication, you may see that it's actually normally quite challenging to put two waveguides very close. Here we can put them less than 200 nanometers. And importantly, the optical losses in these structures here are on the order of just tens of megahertz. So the advantage of the Damascene process is that it's reliable, crack-free. We can grow very thick films of silicon nitride without suffering from the formation of cracks. And also the etching is not material specific. Now, how can you make these circuits very low loss? And we can make them very low loss by doing one more trick, and that is we reflow the preform. So we take the preform of glass and place it in the furnace and heat it slightly, such that actually we take out all the high frequency variations from the etching. And in that manner, we can achieve very low loss integrated photonic circuits where the line width is typically just 6 or 7 megahertz. So this corresponds to kind of quality factors of more than 25 million, okay, in a photonic resonator. And so, for instance, this is an example here of a resonator with a Q of 37 million. And if you look in the background of my picture, you will see actually two spirals on a once European cent. And these spirals actually have a length of 1 meter and less than 3 dB loss. And so with these kind of quality factors, we can dramatically reduce the threshold for our parametric oscillation. And not just that, we can also now directly explore self-injection locking physics. And so this is an example here of work with Michael Gordetsky, where we took a 3.5 semiconductor laser made from indium phosphide, which has an output power of typically about 100 milliwatt, so insufficient to generate combs unless you have low loss photonic circuits. This laser actually is coupled to a photonic chip. The slight Rayleigh scattering you have from the resonator actually causes the laser to be injection locked, and thereby leads to line width narrowing. And the line width narrowing being inverse quadratic with the quality factor. But importantly, we can also generate simultaneously a soliton. And so this is shown in the lower part here. So this soliton injection locking thereby increases the coherence of the pump laser, generates a soliton in a very compact kind of form factor. So, so the low loss now has really allowed us to come very close to this vision I formulated at the beginning, that we can make truly kind of chip scale optical combs. And so how far have we come since then? So this is maybe the state of the art in the field. This is an image here of a collaboration that we enjoyed with John Bowers and Kerry Vahala that we were part of, where we built a optical frequency synthesizer, in this case a free-running gigahertz comb that uses our low-loss silicon nitride. It uses 3.5 and uses this injection locking physics to generate a fully integrated soliton microcomb source. And this source could be used in coherent communications. It could be used for parallel FMCW LiDAR or also for low noise microwave generation. So that's just how far the field has progressed in terms of making combs that are wide deployable. Now, arguably, this is not yet self-referenced. So, so for this, more work is needed, but it's clear that the vision of self-referencing becomes very realistic given the advances and such advances as shown here. Now, microcombs, as mentioned, can have many applications. I highlighted a few: astrophysical spectrometer calibration, coherent communication where you can match the grids spacing, photonic ADC or photonic radar, evidently atomic clocks if they're self-referenced. Recently did work with ZEISS where we looked at the possibility to use microcombs for OCT, where in fact you have noise correlations that can give better SNR in the OCT scans, in the A scans. And also optical frequency synthesizers. But what I want to mention is that the field of microcombs is not just full of possible applications, but there's really some very interesting fundamental physics also to discover. And it's really the combination here of these driven nonlinear systems in highly multimode systems that lead to this pattern formation in conjunction with metrology and this integrated photonics, that gives a very fruitful kind of playground for discovering new nonlinear phenomena. And with this, I'd like to actually close my talk by just showing one last slide, and that is, you can now also, with these very low loss oscillators, think of exploring solitons on lattices. And so what happens if you have highly multimode system like these square lattices, triangular lattices of resonators? How will actually the solitons form? And what we have been quite surprised about is of how complex the physics becomes, not with the full lattice, but just with two resonators already. And what we have observed in the case of two resonators is what we call emergent physics, emergent nonlinear dynamics. So dynamics that cannot be deduced from the single particle description. So the single particle description of the single Kerr-driven resonator we understand very well. There's solitons, dispersive waves, Raman cell frequency shift, all one-dimensional physics we understand very well. If you go to coupled resonators, what we find is that the physics is dramatically different. The reason is you start to have bands because you have symmetric and asymmetric modes coupling. We start to see not just 4F mixing within one mode family, but also intra-band processes. And already at the level of just a dimer, the initial driven dissipative stability chart is vastly more complex. And so the stability chart that I showed initially that had MI, breather solitons and solitons becomes vastly more complicated. It has so-called recurrent dispersive waves, it has soliton hopping, and above all, it has a very strange peculiar property that there is discrete steps in the stability chart itself. And so this just hints at very interesting nonlinear dynamics that can be observed in these driven dissipative systems. And you can now even go one step further and merge it with ideas of topology and make topological bands and look at topological nonlinear photonics. Now with this, I'd like to kind of close and say, yeah, there's a lot that can still be done, like coupled resonators, generating more exotic dispersion landscapes. But above all, I think it's an interesting time right now in nonlinear integrated photonics because of the ability to access new materials, new platforms, and make vastly more complex dispersion landscapes than was possible before. And with this, I'd like to thank all of you for coming so plentifully and for your attention. And I'd like to thank the group, the team, the collaborators, and of course, the funding agencies. And again, thank you very much for the kind introduction and kind invitation.